Welcome back. Today, let's begin the flux aspects. Okay, we'll begin with mass flux. Earlier, we saw some applications of mass conservation, and today we are getting into the actual theme or actual concept of this course, which are fluxes and the forces that cause these fluxes. Let's begin with mass flux. We have already seen that flux of a quantity, a conserved quantity in this case, is the quantity moved per time normalized with respect to the area perpendicular to the direction of movement. For example, mass flux is mass moved per time divided by the area. Suppose the mass is moving in this direction, the area that is perpendicular to the direction of motion of mass, that is mass flux. All our formulations are in terms of fluxes. That makes it easier to formulate across various things, and that is the reason why we are sticking to this quantity flux, and that is the historical development, and therefore, we are sticking to that quantity. In fluid systems, we saw that the product of the density and velocity turned out to be mass flux. Mass flux. The product of the density and velocity is mass flux. You can see the units here, which also give a good indication. The units of density are kilogram per meter cubed, that of velocity meter per second, and therefore, you get kilogram per meter squared per second or kilogram per second per meter squared, which is mass flux. It has wide relevance, of course. The flux of substrates and products in bioreactors, very important. I am just giving you some examples here. The application is wide. Anything that you can think of will have movement of substances, or any dynamic system will have movement of substances, and therefore, flux is important. Some examples: flux of substrates and products in bioreactors, flux of desirable substances in membrane filtration in the downstream processing aspects if you are looking at a bioprocess, glucose flux across the cell, which is essential for the energy of the cell, the product flux in this case, or for example, ethanol moving out of the cell into the extracellular space, and that is what makes it easier to process ethanol. The transport of protein from the site of assembly to the site of function within the cell itself, a microscopic cell. Transcription, translation, and then there are steps after translation. Then there is transport of protein to the area of interest, or the area of its function, to the point of its function in the cell. So, the transport of protein from the site of assembly to the site of function in the cell is of course, very relevant. The mass flux of oxygen from the blood to the organ where the cells of the organ use it, example, and so on and so forth. You can think of various different things. From now onwards, you start looking at various aspects in terms of what fluxes there are, and so on and so forth. That would give you a better appreciation of the applications of this course. The applications are wide, just limited by the sun, I suppose. In a regular class, in a face-to-face class that we have, I give something called a CFA exercise that brings this point across by getting the students themselves to think about the various applications and make a semester long project out of it. That is not possible in this framework, except in a certain minor way, which I think I have mentioned earlier. So, the applications are wide. So, let us start looking at them. Let us consider this experiment first. We have a vessel which has a liquid, let us say water, and we carefully take a pipette filled with ink, and when we reach somewhere in the center, we release a drop of ink, which is colored blue, indigo in this case, into the liquid. Okay. After a long time, if you just drop the liquid, leave it aside, and then wait or come back after some time, a long time, and check, the drop of ink would have uniformly distributed across the entire liquid, just by sitting still, and therefore something has moved the ink droplets or ink molecules from the point of its release to the entire liquid. Okay. The liquid is stationary, the liquid is still. Okay. Still, this will happen over many hours. And what actually causes this, if you recall your earlier physics, is the thermal motion of molecules. As long as there is a temperature, there is motion of molecules, and there is the water molecules are jiggling, hitting against each other, and so on and so forth. Various different motions of molecules. They are interacting with these molecules, the ink molecules, and as a result of these interactions, as a result of these thermal motions, the ink molecules get spread uniformly throughout the liquid. Okay. So, the net effect is the movement of ink molecules from a region of high concentration to others of lower concentration. Initially, there was no ink here, the ink concentration in the other spaces was 0. Here it was the ink concentration in the drop that we let out. So, this is at a higher concentration compared to this, and the thermal motion effectively, although it is all random in all directions and so on and so forth, effectively it has caused the movement of ink molecules from a region of high concentration to the region of lower concentrations, till ultimately the concentrations in all parts of interest become equal. Okay. This is a very classic experiment. There must be videos that you can watch of this experiment. Yeah, you could try that, you could look at that. So, what causes this flux? I think I have given you the answer already. A certain driving force, you can look at this as a driving force. What is the driving force for mass flux? A difference in concentration over a distance, right? Difference in concentration over a distance, and that is actually called the concentration gradient. The variation in concentration over a certain distance is the concentration gradient. Strictly speaking, it is the difference in chemical potential or the chemical potential gradient. If you recall your thermodynamics and so on and so forth, the chemical potential gradient is the driving force for mass flux. But if it is within the same phase and so on and so forth, concentration is a very good approximation for chemical potential. And therefore, if it is within the same phase, we can replace the chemical potential with concentration and we will be perfectly fine. Across phases is a different story, but within the same phase, which means by same phase I mean only a liquid phase, only a gas phase, and so on and so forth. However, if you go from a liquid phase to a gas phase or from a gas phase to a liquid phase and so on and so forth, across phases, interphase transport, then the picture becomes very different. You cannot use concentrations. You know the reason from thermodynamics. It's only the equality in chemical potential that determines equilibrium and so on and so forth, if you recall your thermodynamics. Okay. So, the difference in chemical equilibrium, chemical potential, is the actual driving force for this, but we do not have to be so strict because the concentration works especially within the same phase. Note this, the concentration difference over a distance is primarily or firstly linked to mass flux. Okay. Let me repeat this, the concentration difference over a distance is primarily or firstly linked to mass flux, and there could be many driving forces that cause a much higher flux. For example, if we did the same experiment, but we dropped the liquid, and after dropping the ink, if we stirred the container, the distribution of ink molecules across the liquid would have been much faster. Okay. We all know this. You take, let us say, if you take sugar with your tea or coffee, if you add sugar and let it be aside, set it aside for some time, it is going to take a long time for the sugar to diffuse into a liquid uniformly, so that you feel the sweetness when you drink it. However, all that we usually do is we add sugar, we take a spoon and we stir it. This is providing another driving force. Okay. This is not the concentration difference with distance. This is another driving force which we will look at later. This driving force causes much faster flux. Okay. However, we do not consider it to be primarily linked to the mass flux, and therefore, this is a different driving force. There could be many driving forces that cause mass flux. However, let us first look at the primary driving force that causes mass flux, and that is going to be our theme throughout the course. We are going to see the effect of the primary driving forces first on individual fluxes, mass first, then momentum, then energy, then charge. And then in the last chapter, we will look at the simultaneous contribution of different driving forces to the same flux or different fluxes and so on and so forth. Okay. So, that is going to be the theme for this course. Okay. Now, let us start the nitty-gritty details. You need a certain framework to understand this. So, that is what I am going to give you first, and then if you stay with it for some time, then you will see how it applies to get useful information to draw insights which will be helpful in design, operation, and to begin with analysis, then design, then operation, and so on and so forth. Okay. So, let us begin. First, you need to know something about average velocities. This is something that you already know, but let us look at it in a way that would be helpful to us. Let us consider a multi-component mixture with many species, with many components. Let V I be the velocity of the ith species with respect to stationary coordinate axis. Most of our discussion will be with respect to stationary coordinate axis. I will mention it sometimes, I may not mention it many times. So, V I is the velocity of the ith species. The mass average velocity for a multi-species mixture with n species can be written as, by the standard definition of average, this is the average velocity V hat or V vector, equals, you take the product of the density times the velocity of each species I, and then sum over all those products, divide the entire sum by the sum of all the densities. That is the average velocity. See, you are multiplying the density by the velocity. This is the weighting factor here. You are trying to get a certain average here. So, the weighting factor times the individual velocities divided by the sum of the weighting factors, the standard definition of the average. Let us call this equation 2.1.1-1 to be consistent with the textbook. Species are not molecules. Okay. Species is a concept, it is something like a neighborhood concept in mathematics. It is small enough to be considered some sort of a representation, but it is large enough so that the individual molecule level aspects are not taken into account here. More specifically, a species is a group of molecules with the same species I in a tiny volume element, and we take the sum of individual velocities of molecules of species I, divide by the number of such molecules in that tiny volume element. Okay. So, that is what gives us the average of the species. It is not with respect to individual molecules, but it is with respect to the species. Similarly, the molar average, this is the mass average. Here we multiplied it by the mass density, therefore, we got the mass average. Here the molar average, which we are going to represent by V vector star, can be defined as V star equals, the weighting factor here is concentration, Ci times Vi, take the sum over all species divided by the sum over all species of Ci. So, this is a straightforward definition, recall from your earlier courses, earlier experiences and so on. So, this will we will visit this again and again, we will write various things in terms of this. The very fundamental formulation, there are species, each species has a certain velocity at a microscopic level, and we are working from that place forward. So, it is very fundamental. We will call this equation 2.1.1-2. The velocity of a species I with respect to V or V star is of more interest than the velocity with respect to stationary coordinates. If you are looking at a mixture, you'd like to know how one species is comparing with other species in terms of its movement, right? You're usually more interested in that than its motion with respect to a certain fixed stationary or fixed set of coordinates. And therefore, the comparison is more relevant or more useful. That comparison is given in terms of diffusive velocity of I with respect to v. So, you take V I of any species, subtract the average velocity. This would give you this will give you something called the diffusive velocity of I with respect to V. 2.1.1-3, and you could also have the other one, the diffusion velocity of I with respect to V star. This is with respect to V and this is with respect to V star, V I minus V star, one on a mass basis, the other one on a molar basis. 2.1.1-4. Okay. This is pretty much what we need to be able to start making fundamental sense of movement in a system of interest to us. We have just looked at averages, mass average velocity, molar average velocity of a certain species I, and then we also saw the difference, that is the diffusive velocity of I with respect to V or diffusion velocity of I with respect to V star. These are the only definitions that we have seen. So, let us start using this so that we become more comfortable in its use. To do that, let us look at a problem. Let us consider the disinfection of a lab using formaldehyde vapors. This is typically done in any lab. Typically, formalin solutions, about 40% weight per volume of formaldehyde in water, is used to generate formaldehyde vapors that kill microorganisms in an enclosed space, a standard laboratory disinfection mechanism. Care is taken to seal all windows and doors with duct tape to prevent leakage of formaldehyde vapors when the disinfection is carried out. Okay. The lab is closed, people are warned not to enter and so on and so forth. Then the doors and windows are all completely sealed, gas sealed, and then this is done. The vapors are generated by the increase in temperature due to the exothermic reaction between the added potassium permanganate KMnO4 and formalin, which is the 40% weight per volume solution of formaldehyde in water. Let us assume that we are generating formaldehyde vapors in a long cylinder for understanding purposes. Let us say A is formaldehyde with a molecular mass of 30 and B is air. Let us consider the plane in the long cylinder. Okay, there are various planes in the long cylinder where the mole fraction of formaldehyde is 0.2, 1/5. And let us say at that plane we know V star is 7 units, this diffusion velocity V A minus V star is 8 units, and you are asked to find V A, V B, V B minus V star, V, V A minus V, V B minus V. Okay, these are mass average velocities. This is the molar average velocity that is given here, and you have one diffusion velocities, you are asked to find the others. Okay, just by using the definitions that we have so far. This would give you a good handle on how to use the various definitions to make sense of an actual situation. Let me give you the solution right away. Probably in between the solution I can give you some time to work it out. Pretty much the first problem, one of the first problems in the main theme of this course. So, let me start out first. The molar average velocity is sum of Ci Vi divided by sum of Ci. In this case, you have only two components, formaldehyde and water, right? And therefore, A is just a second, yeah, formaldehyde and air, not water, formaldehyde and air. So, A is formaldehyde, B is air. So, Ca this is 1 by sum of Ci, sum of Ci Vi, that is the way it is written here. The 1 by Ca plus Cb, that takes care of this term, Ca Va plus Cb Vb. And you know that the ratio of the concentration of a species with respect to the total concentration is nothing but the mole fraction. Therefore, Ca by Ca plus Cb is Xa, CB by CA plus CB is XB, we get XA VA plus XB VB. X is the mole fraction. From the problem statement, we know that at plane XA is equals 1/5 or 0.2, VA is plus 7 units. In this case, we are taking the upward direction as positive. And VA minus V star is 8 units, again positive here. From the above, you can get VA is nothing but 8 plus V star is 7 units, therefore, VA is 15 units. Using V star here as XA VA plus XB VB, we know that can you substitute this and get the relevant velocity of interest here. You know VA here, you know XA, XB, you know XA, and because you know XA, you know XB, because XA plus XB equals 1, and you can find VB from here. Can you go ahead and do that? Pause the video here, go ahead, do that, and then come back to unpause the video. Go ahead, please. Hopefully, you got this. V star is 7 units, XA is 1/5, right, 0.2, VA was 15 units, and XB is 1 minus 1/5, it's 4/5 VB. Therefore, if you do the algebra here, VB is 5 units, okay, 3/4 of B and so on and so forth. Therefore, 7 minus, you can work this out, you will get VB is 5 units. Therefore, VB minus V star we already know is 7 units, is minus 2 units. What does this minus mean? It means it is in the opposite direction. Upward direction is positive, therefore, we have the downward direction here of VB minus V star. You can continue with this. I will just go through it, you can work out the various details. We know that the molecular mass of formaldehyde, which is HCHO, as you know, is 30. HCHO, you could take the atomic masses, get the molecular mass. And the molecular mass of air, if you take it predominantly as a mixture of oxygen and nitrogen, will turn out to be around 29. And therefore, V equals the mass average is nothing but 1 by rho A plus rho B, the mass densities, rho A VA plus rho B VB, 2.1.1-5. The mass fraction is defined as mass of A divided by the total mass. If you divide both sides of this equation by the volume, then or the numerator and denominator by the volume, you get the mass fraction of A as mass of A divided by the volume, which is the density of A. And similarly, you have the density of A plus the density of B here, 2.1.1-7. Now, if you substitute this 2.1.1-7 and 2.1.1-5, rho A by rho A plus rho B is WA, rho B by rho A plus rho B is WB, and therefore, V is WA rho A plus WB rho B. I am sorry, WA VA plus WB VB. Here also it is WA VA WB VB. 2.1.1-8. Therefore, WA, if you substitute here, mass of A which is nothing but the mole fraction of A times the molecular mass of A, 1/5 into 30, and you substitute the various values, you will get 0.21. WB is, you know, is 1 minus 0.21, only it is a binary system, there are only 2 components, therefore, that turns out to be 0.79, and therefore, V equals WA VA plus WB VB. You work out the math, it is 7.1 units. And therefore, VA minus V is 7.9 units and VB minus V is minus 2.1 units. We have V here, we know VA and VB from our previous calculations. You substitute it here, you would get 7.9 units plus for VA minus V. and minus 2.1 units in the other direction for Vb minus V. And this is a certain visualization of these velocities. Va was plus 15, Vb was plus 5, Va minus V star was 8, Vb minus V star was minus 2, Va minus V was 7.9, Vb minus V was minus 2.1, okay, or 2.1 in the other direction. So, this is what we are able to find the velocities of these species as well as the diffusive velocities with respect to averages, and that gives us a certain picture of the movement of molecules in that long cylinder, long hypothetical cylinder that we took. Okay. So, this is the starting point of building up or the building up of the formulation itself. Let us stop here. We have been at it for some time now. It is good to take a break, come back in the next class and take things forward. See you then.